I would say of all the students I've ever had in my career, and you can tell it's getting kind of long now, not the hair, but the length of career. Mark is by far the guy that knows more about herps than I ever. What do they say? He's forgotten more about herps than I ever learned. So anyway, he's a bona fide, real, true guy. So anyway, when this project came up, we have, and Mark will do it, but we have to thank Dee Dee for that. Dee Dee was Mark was just a perfect guy to take on this project. So anyway, but I'm not going to steal the thunder because you'll see that. I don't know, what else can we say? Mark's been here a long time. He's one of the COVID survivors. You know, this stuff was a train wreck trying to do all this stuff, and COVID just basically wrecked everything. But at any rate, we're not going to go there because he's here now, so that's all that matters. And like I said, he's got a lot to talk about. He's been a great guy here. Everybody loves Mark. He's just like the nicest guy in the world. He's WYSIWYG, as he used to say in Apples. You know, what you see is what you get. He's just like a good guy. We all love him. And we can talk about at the end that we may get to see, well, we are going to see Mark more here. So we don't leave you guys hanging on that. Dee knows. So without further ado, Mark is going to tell us about all this work he's been doing about rubber boas. And I'm not going to steal the thunder from this gentleman sitting up in the front row here because Mark's going to talk all about that. But when you see this Richard Hoyer, then that's Richard Hoyer right there. So anyway, that's the genesis of this work. All right, so Mark is going to tell, I can't even see this way, the life history of the northern rubber boa, Carina bate. I use the Latin pronunciation. Mark, take it away.
Thank you.
Where am I? I'm over here.
Okay, got it.
Whoops.
And then sorry, was that?
Don't worry about that.
Yeah.
All right. So I'll be going over the life history, and a lot of it's going to be using an over 50-year long recapture data set.
A long time to be a master's student.
I'll see that.
Okay, so I guess I'll just have to click the arrows. So oh, there. Oh,
Do that. That's better.
all right. So the organization of how this is going to work, I'm going to start off with some background information, what the northern rubber boa is, and why study the northern rubber boa. Then we'll get into a small study that goes over the phenology and relative abundance of this species. And then after that, we'll go into some modeling I did to test to see how well some of the models do with imperfect data sets. And so we use some simulations to help with that. And then finally, we'll end up at the main part of this, which is the growth, longevity, and reproduction of the northern rubber boa. And so a way to think of this as, for the background, it's just a drink to start off with. This small study here is an appetizer. And then that modeling, it's like salad with arugula. It's not for everyone, but it'll help set us up for the next one, which is going to be our main entree. So what are northern rubber boas? They're a native boa that's relatively small. They're found in the Pacific Northwest and diverse habitats. And there's only one other species in the genus, which is the southern rubber boa. It is sometimes considered a subspecies, but there is debate on that. Now, this is the northern rubber boa right here. You can see that they're relatively small. These are big adults here. They're under 1 meter in length or under a yard. They have small eyes and a head that's relatively similar size to its neck. And these are both characteristics of fossorial species. And then they have a blunt tail. So you can see the blunt tail here, and then one that is healing right there. It often gets attacked by mice and other animals, but it's a unique feature in our native snake. And if you'll notice, the colors of them tend to be rather drab or earthy colors. So they tend to be tan, olive, brown. And then they'll have belly colors of yellow, oranges, and sometimes cream. And then some of our ones in the Willamette Valley will be modeled with browns or even on rare occasions black. And so another interesting characteristic of northern rubber boas is that there's a lot of interspecific variation in the head scalation. And so this was recognized early on by Steiner in 1890 and Cope in 1900. And then Hoare used it for individual recognition in his 1974 paper. Now, these are 3 male rubber boas from the same site. If you look at this large scale here, that is the frontal scale. And each one of these individuals from the same site have a different shaped frontal scale. And then you can also see that the scales behind that are also different. But this happens with many of their scales, not just those ones. Those are just some examples. And then if you also look at the ventral scales, the belly scales, you can see that there's sometimes these aberrations, which can also be useful. They happen frequently enough that we can use those to help identify the individuals. So that way you don't necessarily, if you want to do a recapture study, you don't actually need to mark them necessarily. So I mentioned that they're native to the Pacific Northwest. They're actually found all the way into the southwestern United States, down to Southern California. They make it up into southwestern British Columbia, and then just over the Rockies in the Wyoming area. As we see there, we have the diverse habitats that they can be found in. I have particularly noted some of the extremes in that area. So on the top right there, we have a site that's near Brookings, Oregon. As far as mean annual temperature, it is the warmest site of all these ones shown here for Oregon. And it is also the wettest. So it gets predictions for that area are higher than what you typically see even in moderate rainforests. And then as we look down here, we get to the drier and drier habitats in Oregon, including one site at Fort Rock State Park, which is the driest site of these photos, and is also the coldest in mean annual temperature. Now, I say mean annual temperature because at this site, if you're to go there in July or August, something like that, it could easily be like 105, 110 degrees Fahrenheit, which is going to be way above what you'd ever see in Brookings, Oregon, which is on the southern coast. It rarely gets above like 85 there in comparison, but year round it stays similar temperatures. And so why study rubber boas in the first place? There are actually few recapture studies on boas in general. Among boas, rubber boas are actually particularly unique. And then for snakes in general, very long-term recapture studies are really rare. And then we'll get into that last one in a bit. And so in doing a little literature review on long-term recapture studies, which are 3 years or greater, based on what I saw for the literature, as you can see here, for boas, we have 4 different studies that I found there. And that's relatively small compared to certain groups like Colubridae and Viperidae, which have a lot of studies. They are also more speciose, so that does make a little bit more sense. And then I mentioned that rubber boas are unique among boas themselves. So this is a dot map of boas throughout the world. And then I've highlighted the genus Carina that rubber boas are in, up here in this tan color. And they go beyond the 51st latitude. And there are no other boas that we know of that exceed that range, except for one example, I think in southern Russia, but the location of that individual is a little iffy. We don't know if it's actually certain or not. So it's our highest latitude boa. But even if that one over there is true, the group of that is Euryx or the sand boas, and we actually don't know a whole lot about those either. And so for very long-term recapture data sets, very few are over 30 years for snakes or even reptiles. And as you'll see here, I've pointed out 5 there that are over 30 years. And then we have one exceptional one up here on colubrids and viperids that is over 50 years. That is a study site by Henry S. Fitch, who died in like 2006 or something like that. But that's currently the longest running recapture data set that I know of for snakes. And so for rubber boas, I had the opportunity to work with a recapture data set done by Richard F. Hoare here in front. That is over 50 years. And this is at that site, Larson, at 52 years from start date. And so having a unique chance to even work with a long-term data set like this is very unusual. And then the other reason is I just like rubber boas. This is a cute little baby. And just like adults, when they are cold and you are warmer and they want to increase their temperature, they'll wrap around your finger or your wrist to get warm. And this isn't a unique case. Rubber boas are actually well liked by a lot of people. And that can be shown by this quote here from Nussbaum, Brody, and Storm. Rubber boas never bite, and are in fact so calm that a favorite trick of Dr. Kenneth Gordon was to wear one wrapped around his wrist as a bracelet while he lectured to his classes at Oregon State University. If you don't know, Dr. Kenneth Gordon was Doc Storm's advisor back in the day. So he had Doc Storm's job like back in the 40s and 30s. And that probably wouldn't fly these days. But anyways, I also do not have one around my wrist. All right. So we covered some of the background information. Now let's get into that small study there on the phenology and relative abundance. And this is going to be focused on Gelatli Uplands, which is near Corvallis. So phenology is the study of cyclic events. So a lot of times these are seasonal or annual events. In herps, activity is one of the common ones that we look at. But another type might be more narrow and might look at just reproductive events or something like that and when those happen in the year. Now, a way to measure activity is to use the difference in absorption rate over time for a site. And so this was done by Stewart in 1968. And so the thing goes that if you have a species that's observed one place at one point in time, and then you don't observe there again, and then you observe it later on, you have periods that you're assuming that they're just changing their activity, not necessarily in decline of the population. And then for relative abundance, this isn't true abundance, it's an index, and it helps standardize data across different data sets or different sites. And so a common example that's frequently used in the literature is to use something like snakes per hour or snakes per traps. And this is used for a lot of other taxa as well, other than just snakes. And so an example with snakes for observation rate is Poirier and Stewart in 2000, using the southern rubber boa species, and then also Brown and Shine in 2002. Now, another way we can look at relative abundance is how many boas observed relative to the other reptiles on a site. This was done in the Poirier and Stewart study in 2000. And so what's been done with the northern rubber boa, in this case, for phenology, in Hoyer's 1974 paper, he found that there's peaks in activity in May and September, but there was concern in that paper mentioned by the author that some of the site visits might have been biased by going during when it's really good to get boas. So we'll take that into account. For abundance, he did general counts for northern rubber boas at that study. And then with the sister taxa, he did relative abundance, comparing it at boas per hour, and also comparing it to the other reptiles in the community. And both these previous studies used artificial cover in their work. So the goal of this study was to look at the phenology of the boas under artificial cover. We're going to take into account the sampling effort for the boas, which is boas per hour. We're also going to look at environmental conditions to see if that has any concerns. And then we're going to look for the peaks for the phenology. And then the other part is to look at the relative abundance of the northern rubber boa, in which case we're going to compare it with the other reptiles in the area, but also look at what we get for the boas per hour. So this is Gelatli Uplands, and so I'll get into the methods here. You can see that there's artificial cover at the site here, and there's a board right there. And so Gelatli Uplands is about 14 kilometers away from Corvallis. This is a schematic of the site that are based off of satellite imagery. I would start at that yellow star there, and we would go counterclockwise to hit all the cover objects. We did this from October 2021 through September 2022 to complete a whole year cycle. Our number of visits were 33, with about 2.75 visits per month. Most of our artificial cover were corrugated roofing metal and plywood, but there were some other ones added on later to compare temperatures, but we're not going to go into that for this study. So for measurements, we looked at the reptile counts that we found under the artificial cover. We even looked at ones that were surface active. There weren't many during the study. For time, we measured start time and end time to get our survey time. And then for environmental characteristics, we looked at air temperature. We looked at the ground temperature under the artificial cover, the temperature of the artificial cover itself. And we would do that with an infrared thermometer and do a zigzag pattern to get the maximum amount, which is allowed or is programmed into the infrared thermometers. So it's an easy way to do it, as the average might be a little bit more difficult. And then we also used Prism to get current and historical temps that are predicted for that area for our studied site, and we looked for aberrations over time. And so from the results from that study, we'll look at our survey temps first. And so this top line here, that's in that gold, that is our temperature of the artificial cover. And as you can see, it gets pretty hot. If you're like me and have a hard time sometimes with Celsius and Fahrenheit, I have the little key up there. So as we get that temperature up to like 50, that's about 122 degrees Fahrenheit. And if we move down and we look at the next line, which is that black line there, that is going to be the temperature of the ground under that artificial cover. And at the very bottom is the air temperature for the site. You'll notice that two of these dots here do not have error bars, which are those vertical bars. And that is because for those 2 months, we only had one sampling event there, and air temperature was only done once per site visit. I did mention sampling or error bars, and that's these vertical bars here. They were done at a 95% confidence interval. And something you'll notice is that most of our air temperatures are under 20 degrees Celsius. And then there's an unusual dip here, which we'll get into a little bit later, for April that we might not expect. And so looking at the phenology of the Northern River boa, we had 3 different peaks in boas per hour, one in February, one in June, and then a smaller one in August. Our maximum boas per hour are 10.53 boas per hour. And then if we looked at a 3-point moving average, this is like a smoothing effect. It gives us more of a single peak, although we have some bumps there. And then, as I noted before, that there's that unusual cold period in our site during April, which we have a little bit of a dip down there. And so we'll look at the aberrant conditions overlaid onto this based off of looking at PRISM data. So looking at the PRISM data, for hot and cold aberrations, so ones that exceeded the 95% confidence interval for the study year compared to 30-year averages, April and May were aberrantly cold, and then August and September were warmer than our average temperatures. For dry period, January to February was unusually dry, April through June was unusually wet, and then also December. And so that April to May period falls into where it was both unusually wet and unusually cold. Now for relative abundance, we've already covered the phenology mostly already. We have 2 peaks that are over 10 boas per hour. A lot of our times where we got rubber boas, we're getting around 2 to a little over 2 boas per hour there. And in comparing to the other reptiles at the site, rubber boas were the most commonly observed. And so this is observed, but not necessarily to the individual level, since we didn't ID unique individuals during the study. And then second to the rubber boas was the southern alligator lizards at 34. By month, southern alligator lizards were found to be the most common in 5 of the months during our study, whereas rubber boas were number 2 at only being the most common during 4 months. For the maximum amount of individuals observed during a single visit, rubber boas are the largest at 7, and the next one down for reptiles is the southern alligator lizards at 3. And so to go into the conclusion of this, looking at the peaks and comparing it with previous literature, as you can see, the peaks for this 1 year study, we had June and August, which are similar to 4 years findings in 1974. They're off by a month, but may not be off too much. But we do have a peak in February, which was not seen in that. And that could be due to that unusual cold period that we had. But it's hard to say with just 1 year's data compared to the many years that were in 1974 paper. For relative abundance, we don't have that for the northern rubber boa, except for this research we did here, but comparing for the southern rubber boa sites, he found that rubber boas at those sites were the most common observed relative to other reptiles as well. Now, some important notes here is that there might be some bias in our sampling times and also the temperatures. So as I noted before, that our sampling temperatures were around 20 degrees Celsius or below. And so changing that bias further on could change what we see in respect to the diversity we see. And then one of the importance of this type of study is for people's research, optimizing the way you can find animals can help you study them, but it's also good in conservation. as you need to notice whether they're present or absent at site, whether they're declining or stable at a site. And so optimizing how you survey for them can be a good tool of that. And so future research should involve potentially checking out these sampling biases. But I've also already accumulated some data for other sites to compare with, but I'm sure there's other data sets that might be out there that I could compare with as well that maybe haven't been published. And then I plan to be doing periodic monitoring of the site and can add to that data set. All right, so we're finishing that part. Now we're getting on to the next part. This is that part where we need to go through, but it's not for everyone. And this is going to be the modeling using those simulated data sets. So I'm going to be using the von Bertalanffy growth function to estimate variables and age using simulated data sets and an adaptive model of it. So this is the von Bertalanffy growth function. So the growth goes there with the blue line. And so it goes to, as you see there, L infinity, which is kind of like a length near like the maximum for the population. So the average length for an individual stop at. T naught there is the x-intercept. It doesn't have a biological reality to it because it is negative age essentially, but it has an effect on when the birth size is. And then K is just how fast that line gets up to L infinity. And so this is a common method used in reptiles and other animals as well. It's used very much in fish growth. And one of the more recent ones was used in Bluen and Demers et al. 2002. Albo and Eichmann used it for aging individuals. And our early look at boa growth showed that it had kind of this pattern of growth. And so one of the reasons for checking the models against things was because there are some problems with the data set, which they're great data sets, but age bias was a concern, along with the low count of known aged individuals. Now, age bias isn't a surprise. If you study an animal that lives beyond your study period, you're likely to get an age bias in your thing, unless you're able to age them in other means, such as skeletal chronology, which can be expensive, but also may have issues of its own. One positive to the data set is that there's a lot of unknown age recaptures, so we might be able to use that to impute data into that to create estimated ages. And so one of our goals for this is to look and estimate ages with the problems that arise. And so I don't have any nice field photos to show for this one. So these are going to be snapshots of my images that I sent out while working on this project related to usually R code. So one of the first things I had to do is I had to create a simulator. So I created an imperfect recapture dataset simulator. I made a varied and a near fixed population. An example of the varied population is on the top, and then the near fixed is on the bottom. Each individual in that simulated population was allowed to have their own unique growth variables. So these variables were chosen based off of actual BOA data, and they were allowed to be chosen randomly within certain constraints. And for each of these populations, I had them go out to 400 individuals. And to create our biased sampling, for age bias, I had two different ones set up. The 9-year age cap and the 19-year age cap. We only used the 19-year age cap for one of the combinations, but we used the 9-year age cap for all of them. And so we did 15 individuals to simulate our low count of known age individuals. We varied the amount of recapture data that individual had for the small group at 40%, 60% for the medium group, and 80% for the large group. The rest of the data was separated to be selected for unknown aged individuals, and we selected 5% at random of that, which roughly equaled 137 individuals. And then we would run these sampling models 35 times. And we're going to focus mostly on the varied population because the varied population tends to be more of what we see in reality versus the near fixed population. And so the known age model and the estimated age model are something I'm going to be using a lot here. And so they're abbreviated CAM and EAM. And I will start using those a little bit more frequently as I go through. And so the known age model is basically just the von Bertalanffy growth model with the age estimation associated with it. The estimated age model uses imputation of data based off that known age model. And so how that works is that you split the data into known and unknown age specimens. You create the known age model as a scaffold, so that's that standard von Bertalanffy growth function. Then you align the model's age estimates to your unknown data. And then once it's assigned, you use that to do your recapture ages by adding that estimated to it. Remove the aligned data point, so breaks it away from, so like makes it a little bit more independent of that alignment, but not necessarily fully. And then you rerun it to get your estimated age model. And so one of the things we wanted to look at is we wanted to compare the variables compared to what's the actual populations, averages, and max and min. And so for L infinity, we looked at the actual value. So looking at the difference between the true and the estimated. This is because L infinity has more of a realistic biological and interpretable evidence. So if you look, you're like maximum length at like 20 inches, yeah, that you can interpret that well. Whereas K and T naught are not as interpretable as those. We're going to focus more on the model, comparing the models and the age estimations. And for that, we're going to use the median with the first quartile and third quartile for our samples. So we're going to compare it to the population mean with the min and max of that. And then age estimation, since that is a relatively interpretable variable, we're going to use difference for that one as well. So we're going to focus on those. And now time for the results. Like I mentioned before, these are texts I sent out regarding my work with YAR. And there were a lot of times the model did not work, but when it finally did, I was very happy. And so this is what one of it looks like. And so as you know here, there's lines and ribbons. Ribbons are the lighter shade around it. So the true population is going to be the black line, and the min-max of that is going to be that gray shaded area. And then we have the CAM, the known age model, which is red with a lighter shade, and then the estimated age model with that blue color. Now it's kind of hard to see how these lines differ, so it probably worked best if we actually zoomed in on it. And looking closer at this, we can see that the CAM estimate is much closer to the true model estimate, or the true model, than the actual EAM. Now, although the EAM is within the min and max of the true population, so it does an okay job, but not as good as the CAM in this point. And if we look at age estimation, we have the known age model here. We have the large sample size, the large and high age sample size, the medium sample size, and the small sample size. And as you'll notice that with the known age model, you get kind of just this positive error here in estimating age. But if we look at the estimated age model, you get that positive error, but then after a certain point with those really large individuals, you get a lot more negative error there in the age estimations. And so there's a lot of data points here. So let's look at some numbers of those larger individuals. So looking at the medians of these towards those larger individuals, we can see that the EAM here tends to have that negative median there, and that is an overestimation of the age. Whereas the known age model there has more positive values, which is an underestimation. Now I also have the absolute value of the medians to show more of the true error of these, because if you have like an average between -1 and 1, they'll give you 0, and it'll look like 0 error. And so this gives you what it actually is, and that you so having a -1 and a 1 for error would give you like a value of 1 for that point. And as we see there, the known age model does better with the error compared to the estimated age model. And so for conclusion, this was me telling a friend of how long it took, or telling about doing a model, and that's how long it took, and well, very long time. So a general comparison. The no-age model generally performed best on all of the things we looked at in variables and most of the growth considerations. They both performed relatively well, but the only time like the EAM really seemed to outperform the no-age model is in estimating L infinity with the varied population. So the recommendation of using this at this point is to use only the no-age model or to use both of them, the no-age model and the estimated age model, possibly as like a lower bounds and upper bounds. So for some assumptions, this current model assumes that all individuals have true von Bertalanffy type growth. And also sampling within those bias categories that I made is at random, which may not be what you'd see normally in reality. Normal in reality, if you have like a 90-year age cap, you might see a lot more individuals in the area of like 1, 2, and 3 versus towards the edge there. Imputations, such as the estimated age model, where you take that value to help add in some information that you're missing, is usually only meant for a small amount of data, but it actually, what I used it for was to be the overwhelming amount of data. So scaling that back might help a bit. And then there's also more complicated types of imputations, like multiple imputations, which take into the issue of it being more variable than single value. So one of the future things is to look at multiple imputations and how it affects it, using smaller amounts of the imputated data, and then also test it with the Gompertz or a logistic model. So not true von Bertalanffy growth, and see how that affects it. This is an example of the Gompertz growth. It has a slight lag here, which the von Bertalanffy doesn't have. And there is some evidence that at least one of the populations might have that type of growth. All right, so we got through the salad. Let's get to the growth, longevity, and reproduction. And so this is the one that uses that over 50-year data set. Now a little bit about snake life history. Well, and a lot of resources I looked at, it turns out we lack a lot of good information on the demographics of snakes, with the exception of a few species. And this greatly affects how we know snake populations and even conservation at that. And here are some of the examples of the demographics that we do poorly at, including population sizes, age distributions, longevity, and so on. If you took ecology here, you probably had to fill out a life table. You probably couldn't fill out a life table with most of our snakes we have in the US because we lack the information. One demographic that we do have good information on is litter size. And this is probably because you can get litter size data from observed specimens pretty easily. Now, as far as the northern rubber boa is concerned, some work has been done on it. So you might notice the theme here that there's one author in particular that does most of the work for this species. Porter in 1974 looked at size distributions of the northern rubber boa, looked at reproduction size, and also looked at sex ratios in populations. And a future study in 1992 with Doc Storm, they looked at litter size, the minimum age of reproduction, and also the minimum size of reproduction and the reproductive frequency. Both of these studies were done with Northwest Oregon populations of the Willamette Valley or the adjacent Coast Range. And so some goals from this is to look at, well, the von Bertalanffy growth formula of the northern rubber boa. And we're going to use that to estimate ages of the individuals that are unknown to help find out longevity. We do have some known ages of longevity that are up there in age. And then we also want to figure out the lifetime reproductive success. So this is the amount of babies the boa can have in its entire lifetime. To do that, we'll need to look at reproductive lifespan. Now, we did look at geographic variation, but this is a part that I'm not going to go into too much. A lot of these values, we're going to look at a case study as an example. And so, as a reminder, we're going to focus on these parts. I will have the information for geographic variation if that is what you're interested in, but I can answer questions about that after the talk. All right, methods. Well, I didn't really collect any of the data for this. A lot of it occurred before I was even born, including the RAB site started in 1971, Larson, which is the longest running site, that is over 50 years and probably still continuing. Chapman started in 1969, and then Cardinal Pitt. And so there's the other sites there, but we're going to be focusing on these Willamette ones. And these are the samples of the adult females that were caught in the population. So these don't necessarily have recaptures to them, but this is the number of adult females that were, or females that were found in the population. And so these research sites, these are the different research sites. The lime green there is the Willamette Valley ecoregion. And so those are the ones we're going to focus on. You can see a little bit closer up on the inside. If you know what your Oregon counties look like, that one is up there in Benton County. And so there is highlighted those three up there. And one of them actually occurs in what is now South Corvallis. So I mentioned that we're going to use this case study. And so why should we look at this case study? Well, during this individual's initial capture in 1971, it was a very large female at 27.5 inches or 69.9 centimeters. For a rubber boa, that's very way up there in size. It was a decent weight at 130 grams. But more importantly, its last day in the wild was in 1989, and that is 18 years from its original capture date. It was then brought into captivity, and in captivity, its last reproductive event was in 2000, 29 years after its initial capture, and then it died in 2006, 35 years after its initial capture. And so we're going to use those numbers that I just showed you there to calculate these different points of interest, including wild lifespan, maximum lifespan, and estimated reproductive lifespan. And some other ones we want to look at is mainly the lifetime reproductive success, but we'll have to calculate the lifetime reproductive events, so how many times it reproduces to find that out. And so, like mentioned, we'll be using the von Birch length of growth function to look at this, and we'll be focusing on the Willamette Valley ecoregion. And so we'll use the known age model, or CAM, for the lower bounds, and the estimated age model for the upper bounds. For reproduction, for frequency, which we'll need to know for lifetime reproductive success, this was done through data of females that had repeated years of findings during points of when they could be popped for ova or embryos to see if they're likely to be pregnant that year, and then also have bounds of birth events. And so we'll use the median value for this. And so one way to think about frequency that has a birth event, that individual for a 3-year frequency would have a 1 year where it gets caught, but no reproductive signs are seen. Another year where it's recaught, no reproductive signs seen. And then that following year, 3 years after that, is going to be when you get that reproductive event. And so that's how those individuals were selected for that. For litter size, we'll use the median litter size for population. Information here for the geographic variation, if that's what you're interested in. And then reproductive size, we'll use the minimum and first quartile for the population that we have reproductive events for. And then similarly, there is geographic information with multiple linear regression and AIC model selection if you want some of that information. So getting into the results. So this is the known age model for the boas, and the Willamette Valley population there is in that lime green. So I have the red arrow over there. Some things I should note about this is that the residuals were concerning in this model. So it had unequal variance and also a non-normal distribution of the residuals. This could create some issues in our estimation, but we don't know how bad those issues can be. So take that with what you will. And as you'll note, I put asterisks around ones that were significant. If you're interested in the geographic variation, such as in this case, some of it is significantly different in its growth compared to the other two populations. Now for using that estimated age model, it did a little bit better on the residuals. It only had unequal variance, but I'm not sure if, how well that can deal with what goes into estimated age model. Again, the line green there shows the population we're interested in, and the solid dots are known age, and the hollow dots are the estimated age individuals. And so using both of these, we'll estimate the ages. And so for the estimated age of initial capture for that female was 20 years for our lower bounds using the known age model, and 36 years for the estimated age model. Now, I will point out that these are actually the maximums that these models could estimate for ages, because she is well beyond the L infinity for those models. So she is an outlier even in that sense. And then if we're to add these together, for the estimated wild lifespan, we're looking at 38 to 54 years. Estimated total lifespan, we're looking at 55 to 71 years. So that includes that period of time in captivity. All right, and so here's the one where we have the sizes of reproductive females, so females with reproductive events. The size measurements of these females were within a few months of them giving birth. And for the minimum, we have this data point here for the Lamb Valley section at 53 and some centimeters total length. And then for the first quartile, it's not visible on this graph, but it is 61 centimeters. Like I said, there is information there if you're interested in the geographic variation, and I'm available for questions afterwards regarding that if you're interested. So we can use those measurements to estimate the min and first quartile with the different models. And so with the known age model, we're looking at 8 and 16 years for the estimated first time of reproduction, and the estimated age model 7 and 12 years for the first age estimated or first estimated age of reproduction. Now for other information on reproduction, neonates, we have here in the lime green is the Lamb Valley population with a median of 4 neonates per litter. And then for reproductive frequency, we have 3 years for the Lamb Valley ecoregion, which we'll use to calculate the next one, which is reproductive lifespan. And so for reproductive lifespan, which is all the years that an individual can be reproductively active, or at least we would assume can be reproductively active. And so for our lower end of the range, we have 33 to 41 years. And for our upper range, we have 58 to 60 years. Then calculate the amount of reproductive events likely. So with that 3-year frequency, we get our lifetime reproductive success when we times that by the litter amount. And so for lifetime reproductive success, we have 44 to 52 neonates, and on the upper bounds, we have 76 to 80 neonates. So getting to the conclusion and comparing with what we know. For wild lifespan, we're estimating at 38 to 54 years. Maximum lifespan, 55 to 71 years. Age at reproductive maturity, I was looking between 7 and 16 years, depending on the model. And then we estimated reproductive lifespan going around 33 to 60 years. And we just covered the neonates, so I won't go over that. And some of these ages seem really well up there. And you might wonder if this is surprising. Well, for me, it's surprising and not surprising. I had the chance to input this data, and so seeing that there's several individuals with over 20 years of recaptures, and they were big adults when they were first caught, doesn't surprise me that we're getting ages, even some of the ages coming out of the estimated age model. Even Hoyer's estimates, without doing these fancy math and figures I've been doing, got similar results with estimating the age at initial capture at 15 years minimum, but likely over 20 years. And he also estimated the last age of reproduction between 49 and 69 years. So what does this all mean? Well, these are classic traits of a slow life history. So having being old at its first reproductive time, having low litter sizes, and then also having infrequent reproductive events. Now, on top of that, we might have the longevity record for wild snakes. The current record holder is a green whip snake, which is a Eurasian species at 33 years. Use skeletal chronology to estimate that age. Our estimated ages here that are over that are 34 and 236 ones. 2 of those had recaptures over 20 years, and their initial capture size was they were adults and sometimes large adults at that point. So some future work with Hoyer's rubber boa data sets that I hope to do is look at population dynamics, particularly with the Larson site, which has had historical disturbances in it. And then also add to the phenology based off of those data sets as well. We'll be able to add other geographic areas that we don't know much about, such as the Northern Basin Range and the Cascade Mountains. So that is finishing up here. There's still a lot we don't know about our native snakes, including northern red boas, and hopefully that will change in the near future. And hopefully I've added to that. So to start off, my first acknowledgement is actually my first pet snake was a northern rubber boa, and it was given to me by my uncle, probably regretfully allowed by my parents for me to keep it. And it is actually what led me to connecting with Richard F. Foyer when I was a teenager in the first place. And it also led to many other connections down the line, including Doug Knudsen and Alan St. John, which were great mentors to me early on. And then future folk like Chris Rombo, Bruce Purry, someone that might be familiar here, Bob Mason, and also my wife. My wife is actually a particularly good mentor when it comes to art programming because there wouldn't probably be any modeling if it wasn't for her because of all the problems that happened along the way. So, but there are many other people here. My committee, so Katie Duggar, G.D. Olson, Doug Robinson, IB staff, which do things behind the doors that I have no idea what happens, but they make things probably so smooth that I don't notice, which is probably the best. But I'm also probably very sorry for all the headaches that caused them. Folks from SMAB, like Mark Hayes, who's also here, Teal Waterstrap, they've always been encouraging and also would discuss research. Teaching mentors, so many teaching mentors. Devin Quick, particularly because I've worked with her the most, and she's been quite inspirational in my teaching career. Lab mates, particularly Dave Hubert and Alice Welch. Dave was one of the few people that I had to talk science to during the pandemic when basically I wasn't talking to anyone. And then Alice Welch actually helped out with our phenology study and collecting data and entering data. The old Herp Club people, as we've talked and gone out into the wild a lot together, reduced some of the stress and talked a lot about herps, including research. Fellow IB graduates who have always been nice to me. I'm glad there hasn't been any like bullying or anything like that into college. They've always been nice and welcoming and encouraging with this trip. Funding was provided a lot by Integrative Biology through an assistantship. U.S. Forest Service also helped fund some of my summers, and also Amphibians and Reptile Conservation provided some funding as well. There are probably many others that haven't been mentioned here. Actually, I think I might be forgetting one. Oh, yes. Richard F. Foyer, who has done great work with rubber boas, sharp-tailed snakes, and has helped people with various research projects longer than I've been alive, providing specimens, helping them get their samples, taking them out in the field, and not only people that need it for research, but people just coming to town to find their first rubber boa, their first sharp-tailed snake. I still hear about every year or every other year about some kid that got to see their first sharp-tailed snake because Richard was nice enough to take him out to one of his sites. And with that, is there any questions?
Hey, just for you rookies here. So as is our tradition in academia, we'll open the floor for questions, except for his committee where we'll do an extra special grilling in private. So all of you guys weigh in.
I have one comment about a serious flaw in your data. You're 2 years off on my age.
Hopefully on a good end.
Add 2 years to the 88.
Recommending that assumption of mine.
Since I cannot hear well, the Patrice Road data, was it 1 year or 2 years?
1 year.
1 year.
Yeah.
Okay. And the only thing I comment is that that particular set of data is probably maybe somewhat atypical because it varies with each year and temperature and weather.
Yeah.
And you had high observation in February and low in April and May.
Yep.
And it's usually just the other way around.
Yeah.
Although this year they were there in January, February, and I haven't gone out this month.
Yeah. And so that actually might be that might be the more trend that we see as we get these I shouldn't say freakishly cold spells, but these unusually late cold spells that we maybe don't normally see. So we'll find out as I keep going out there, and assuming I take good records and don't just enjoy myself.
I'll leave it to more serious questions.
So not an animal person. So one is when you're sampling, do you always go out to the site at the same time of day? Or how do you decide when you're gonna go?
So yeah, sampling time was a concern for one of our biases. It was usually a similar time of day, but it did vary, particularly with the summer and the coldest part of winter. And so we tried to make it to where it was reasonable to find snakes for that day in general. So for like summer times, we tend to go a lot earlier than we would in spring and fall. Spring and fall, I think our averages were usually around 10 to 11 a.m. And it takes about 30 minutes to complete, so not too long. We have one winter or late fall time where I think we started at like 1 or 2 p.m. because, well, it was just really cold that day and didn't get above like 53 Fahrenheit that day. And then like some of the summer examples where I went, I think at like 9 a.m. or something like that. It already heated up pretty well, and the high for that day was going to be like high 80s or mid 90s. And if you go out there when it's like 90 degrees, you might get one southern alligator lizard that for some reason decided to bake itself under the tents. But yeah, usually capture low. And so that's part of the bias in surveying that hopefully can piece out over time.
So second question is just sort of, well, maybe two. Like, what do you think the range is for a snake? So like how far will it travel or live? And then given that, how do you decide how many covers should be in an area?
So for range, we don't actually know a whole lot about a range, how big a range is for like a home range is for snakes in general. There are some cases in British Columbia, they looked at ranges and boas and they had a relatively high fidelity foresight and didn't move too far away. But that may not be as applicable down here. With some of Porter's data sets, we do know that females at some places stayed around for a long time at those sites because they were recaptured over 20 years. But there were years where they weren't found, and I have no idea where they went off to. They might have still been at the site or they might have left the site. But we don't have good information on that too much. I know there have been radio trackings done for river boas, but it was only done with adult females, which could bias that because we've seen in some other snakes that males will tend to travel further than females. And then for how many cover objects placed out, we don't have good information on that, but you would assume that there's a point at which you have too many cover objects as far as time. So like you'll max out on the number of snakes you'll find and still have more cover objects. Don't know what the maximum is or the ideal spot, but it probably varies per site. I know that like some sites with only a few cover don't work out well. A lot of sites that I've been to have anywhere from 10 to like 50 cover objects and tend to have a little bit better luck that way. But I mean, at the site itself, you'd have like these dead areas and there are certain cover objects that were much more likely to have individuals under it, which was another issue, specifically when it comes to sampling, was clustering. And so we don't have good information on that, and it'd be good to look into in the future to figure out how many of which different types of cover objects can be beneficial for a study. Yeah.
Great work. This is really interesting. I was wondering, given that the rubber boas tend to have these like unique scales, I was wondering what you thought about using like citizen science photograph data sets to answer some of these questions about snake phenology and abundance.
Yeah, and so if you can get that, you can. It's a little hard sometimes just off of head scales, but you can probably, as long as there's not like a really diverse amount of individuals in that population, with the different size of the head, you can at least identify a good amount of the individuals that way. And so using citizen science could be a good way to do that. I've actually looked for other animals that may have unique markings through iNatural's photos to see if like, well, I saw this giant salamander a few weeks ago. I wonder if any of the other people that went up to Mary's Peaks also saw it. So it's possible. There's an issue sometimes is that with can happen with citizen science or just taking people out to research sites is that collecting can also be an issue. To where you had an individual and well, someone decided to keep it as a pet, which I think currently under state law is not allowed, but used to be allowed. doesn't stop people necessarily. That answer, okay.
Does the amount of snakes that you are able to observe, does that have to do with also the predators or getting them? Does that change year by year or?
I mean, I assume it would change, like predation effects. We don't know too much on predation of rubber boas as far as like the overall effect of it. We know some known predators of them, but we don't know like how many each year are affected by coyotes getting them at night or anything like that. So yeah, we don't have a good information on if we get drops from predation in natural environments. Yes, on another hand up. Yes.
Can you say anything about the stability of this population based on your data set compared to 50 years ago?
So for a lot of these, it's hard to do, but for the Larson site, we might have enough data to look at stability in population. But that's mostly through looking at how well recaptures do per site visit. And for the Larson site in like 98 or 99, there was a timber harvest event. And captures in general went down, which could be due to cover being moved. But when numbers finally started getting back upwards, recaptures of those individuals that were present before was very low and then didn't really show up again. So we had the newer recaptures tend to be ones after the event, with the exception, I think, 2 individuals, which was unusual compared to before for similar amounts of site visits. So we can look at that if we can quantify recaptures for each site visit, but I haven't gotten too deep into the woods there yet.
We all get to leave with a rubber boa.
I can't say anything while being recorded about that.
All right, if there aren't any other questions, let's give Mark another round. Those staying around, we'll either have a celebration after the exam or we'll have a commiseration.